Hello, my name is Evan Chang, and today I'll be explaining the OMC problem of the month for the month of October 2022. So the problem is as follows. To find a convex quadrilateral P on a plane, in a turn it is allowed to take some vertex of P, move it perpendicular to the current diagonal of P not containing it, so long as it never crosses that diagonal. Initially, P is a parallelogram, and after several turns it is similar but not congruent to its original shape. And our goal is to show that it is a rhombus. So let's start by seeing what happens when we apply a turn, right? When we apply the operation. And our main goal to solve the problem is to just make sense of this really weird, complicated operation that we're applying to the quadrilateral. So often when we're dealing with some kind of weird, complicated operation that's not very well behaved, our goal is to look for an invariant. And an invariant is something that stays the same. An invariant stays the same no matter how many times we apply the operation. So with something that's not very well behaved, we can concentrate on an element of the setup that remains the same in order to deduce certain facts about the setup that will help us solve the problem. So that's essentially the basic idea of an invariant. So here, let's say we're moving vertex A, for instance, and ABCD is the parallelogram that we're dealing with. So in a turn, we're allowed to move A perpendicular to the diagonal BD. We're allowed to move A perpendicular to the diagonal BD. And let's say that the foot of A to BD is P, right? So P remains the same as A moves along, right? P remains the same as A moves along the diagonal. So the next thing we should observe is that dp squared plus pa squared equals dA squared, and bp squared plus pa squared equals ba squared. And so now you might notice that we can cancel out pa squared from these two equations by subtracting them. So you'll basically get something like bp squared minus dp squared equals ba squared minus da squared. And now we've done something that's pretty cool. We've canceled out pa squared, and pa squared is the only thing that changes. It's one of the only things that changes when A is moved. Meanwhile, BP and DP are both fixed because as we move A along, P, D, and B are all fixed. So BA squared minus DA squared is also fixed. So BA squared minus DA squared is fixed while we move A along. However, this really isn't the invariant we're looking for, because we can also move other vertices like B, C, and D. If we were only allowed to move A about and not any of the other vertices, if we just let all the other vertices be fixed in place, then BA squared minus DA squared would be a valid invariant. However, we need to find a different invariant that accounts for cases when we move the other vertices. So let's see what we can say for the other vertices. So when we move B, then similarly to how we analyzed A, you'll be able to see that instead of BA squared minus DA squared being fixed, you'll be able to see that CB squared minus AB squared remains fixed. And when we move C, we'll be able to see that we'll be able to see that DC squared minus BC squared is fixed. And when we move D, then we'll have that AD squared minus CD squared is fixed. So we have 4 different things that are fixed depending on which vertex of A, B, C, D we're moving, right? So if we move A, then there'll be one thing that's fixed. If we move B, then there'll be this other thing that's fixed. And we basically want to kind of combine all of these. We want to combine all these things that stay the same into one big invariant. So we want to find one common invariant that stays the same no matter which of the vertices we choose, which of A, B, C, D is chosen. So this is the main insight of the problem, I'd say, trying to combine all these different invariants together. But if we spend enough time on this, maybe you'll get lucky, maybe you'll find some sudden insight, or maybe you'll just bash your head on the wall for a bit. But eventually, hopefully, you'll find a common invariant that holds no matter which of A, B, C, D is chosen, combining all of these observations that we've found so far. And this common invariant is AB squared minus BC squared minus CD squared minus DA squared. No, my bad. AB squared minus BC squared plus CD squared minus DA squared is what I meant. So why is this quantity an invariant? So let's think about it. So let's say we move vertex B. Then we'll see that A B squared minus BC squared is fixed as we move B, and neither of CD or DA is affected, right? Let's say we were moving something different. Let's say we were moving vertex C. Then negative BC squared plus CD squared would remain invariant by the observation that we had earlier. And once again, neither AB squared plus DA squared are affected by the movement of C. So once again, our common invariant holds. And you can extend this for all of the vertices. No matter which vertex we move, there will always be two of the terms here that will remain unaffected, and the other 2 terms, their sum will remain the same, even if the individual terms of that sum will be changing. Their sum will be the same. So that means that this invariant will hold no matter which of the vertexes are chosen, whether that's A, B, C, or D. So now let's come back to the main problem. So initially, P is a parallelogram, and after several turns, it is similar but not congruent to its original shape. So let's say that P is not a rhombus, for instance. Let's say that, without loss of generality, that let's say AB is bigger than BC, all right? So let's say that after several turns, we get a parallelogram that's similar to A, B, C, D, but scaled by a factor of Q. Let's say this is scaled by a factor of Q. So but since we applied the invariant, right? The invariant, this quantity over here, it has to be the same across A, B, C, D, and its scaled version. Let's call it A prime, B prime, C prime, D prime, right? However, since A prime, B prime is 1 over is Q times AB, or B prime, C prime is Q times BC, basically what we found is that the quantity evaluated for A prime, B prime, C prime, D prime is basically Q squared times the quantity evaluated for A, B, C, D, right? The quantity evaluated for the scaled quadrilateral is Q squared times the quantity evaluated for A, B, C, D. And since AB is greater than BC, and similarly CD is greater than DA, this is greater than 0. So that means that for the invariant quantity to be the same across both rectangles, that Q must be equal to 1, essentially. And this means that A prime, B prime, C prime, D prime has to be congruent to ABCD, because the scale factor has to be exactly 1. So now you might notice, why doesn't this hold for rhombuses, right? Why doesn't it hold for rhombuses? Why can we scale up or scale down rhombuses at our will, basically? And this has to do with the fact that in a rhombus, right, the invariant is actually 0, right? Because if AB equals BC equals CD equals DA, then AB squared minus BC squared plus CD squared minus DA squared is equal to 0. So the invariant quantity is equal to 0. So we can scale this by whatever we want, and it will still be 0. So that means that A, B, C, D can hypothetically be scaled up by whatever quantity we want, and the invariant will still be 0. So we can't outlaw this in the same way we could outlaw this when ABCD was not a rhombus. So in conclusion, we found an invariant, and we showed that initially, if P is a parallelogram that's not a rhombus, by changing it to a parallelogram similar to it, in order to satisfy the invariant condition, we must have that new parallelogram be exactly congruent to the original shape. So that finishes our work on this problem. Hopefully you learned something from this video. Join our community Discord for more information and materials, and I'll see you in the next one. Have a good day.